Okay, so this is Chapter 11, Solutions, and today we're going to talk about solution composition, energies of solution formation, factors that affect solution formation, and possibly vapor pressures of solutions. We're going to start with some important terminology. Some of this is a review of important vocabulary, but nonetheless we need to go through it. So the first thing that we're going to talk about is solute. What is the solute? That is the substance being dissolved. And this is usually present in the lesser a quantity of the two, between the solvent and the solute. And then the solvent is the thing that is doing the dissolving. And this is usually greater in the, present in the greater quantity. Remember that when the solute dissolves in the solvent, you are creating a homogeneous mixture, meaning that it is consistent throughout. So if I dissolve salt in water, the salt particles are distributed evenly. So all solutions, okay, all solutions are homogeneous. And solubility is a term to describe the amount of solute in a given amount of solvent. And this is usually measured in grams of solute per 100 grams of solvent. Okay, so let's talk about various types of solutions. I'm just going to pick a couple. So you have brass, which is an alloy. So let's talk about various types of solutions. I'm just going to pick a couple randomly and talk about them. First we have brass, which is an alloy of copper and zinc. And both of those are in the solid state. So the solute is a solid, the solvent is a solid, and you wind up with a solid state of solution. And they do this by basically melting them down, but you're starting with solids. Carbonated water, soda, you're very familiar with that. You know that the state of the solution is liquid. The state of the solute, however, is a gas. You're putting the CO2, dissolving the CO2 into the liquid, which is the flavored water, and that is in a liquid state, but you wind up with a liquid. And let's look at seawater sugar solution. You know that you're going to have a liquid in the end. Your solute is your sugar, and that's going to be a solid, and your solvent is a liquid. So you can see here that depending on the various states of the solute and the solvent, what type of solution can you form. We have solutions that are gases, liquids, and solids, which sounds weird when you say the word solution. We're going to talk about and review 4 different ways to measure concentration. Molarity, you are very familiar with, is moles over liters. Molality, this is a new one. It's the moles of solute, again, just like the same in the numerator as the molarity, but it's over kilograms of solvent. Mass percent, you're familiar with, mass of solute over the mass of solution, and that should be times 100. And then mole fraction, you're also familiar with. That's the moles of A over the total moles. And if we think about it, mole fraction is actually like a percent because it's the part over the whole, but it's just in the decimal form. All right, so let's review all of these with a problem. The density of isopropyl alcohol, which I'm going to call IP in this problem, C3H7OH, is 0.785 grams per milliliter. A sample is made by mixing 20 grams of isopropyl alcohol with 40 grams of water. What is the molarity, the molality, the mole fraction, and the mass percent of this solution? Whenever you get a problem like this, the easiest way to do it is to find grams and moles of both the solute and the solvent, and then do the math. And we know that for the most part, you guys can do math. So let's see what we have. We've got 20 grams of IP. So we know the grams. So let's get this into moles. So we know that 1 mole of IP has a mass of C3H7OH is going to come out to be about 60 grams. My grams are going to cancel, and that's going to give me 0.33 moles of IP. Let's do the same for the water. I've got 40 grams of H2O. We know that 1 mole of water has a mass of approximately 18 grams. My grams cancel, and that's going to give me 2.22 moles of H2O. So while we've got our moles, why don't we just do our mole fraction very quickly? So we've got the moles of IP. Remember that that little funky X is moles. It's actually the symbol chi. So we've got 0.33 over 2.22 plus 0.33. And that's going to give us 0.13. There's no units for mole fraction. It is what it is. And then to find XH2O, I could do the same thing. I could put 2.22 over 2.22 plus 0.33, but mole fraction is always out of 1. So I'm just going to take 1 and subtract 0.13 to make things easier on myself. And that's going to be 0.87. 0.87 is the mole fraction on that. All right, so now we need percent. We can do percent next. That's pretty easy. So percent is going to be part over whole times 100. So the percent of IP, so that's 20 grams of IP over the total is going to be 20 plus 40, which is 60 times 100. And that's going to give me a percent of 33%. Okay, so we have molality and molarity left. So I'm going to squeeze in molality over here at the bottom. So molality is equal to moles. So we have 0.33 moles of IP over kilograms of solvent. Well, the water is the solvent, and we know that 40 grams, if we divide by 1,000, is 0.040 kilograms. So that's going to give me 8.25 molal, which is a small m. Okay. And then molarity is equal to moles over liters. So there's a small problem here because with our liters, okay, we know that they gave us a density. So we have to account for that. Now, what I do want to point out was that they gave us the density for isopropyl alcohol, but not the density of water. So we're going to assume that this is at room temperature. So the density of water at room temperature is 0.9982 grams per milliliter. So I'm actually going to do these separately because we have to use the density of water on the grams of water and the density of isopropyl alcohol on the grams of alcohol, and then add the two together to get the total milliliters of the solution, which we can then change to liters. Most problems read as the density of the solution. So in that case, you can just take the total grams of solution and apply the density factor to it. But in this case, this problem didn't read that way. So I'm just going to do it up here so you can see what I'm doing. I'm going to take the grams of isopropyl, which is 20 grams, and we know the density is 0.785 grams per milliliter. And that's going to give us a total of 25.48 milliliters. And then I'm going to do the same thing with the water. We had 40 grams of water, and we know the density of water is 0.9982 grams per milliliter, and that's going to give us a total of 40.07 milliliters. So if I add the 2 milliliters together, I am going to get 65.55 milliliters. So let's come down here. We've got 65.55 milliliters. So I'm just marking that. Probably could have left a little bit more space here. So we have moles. We know our moles are 0.33, and we need this in liters, so that's going to be 0.0655, and that's going to give us a molarity of 5.03 molar. Okay, we have a second problem here. They give us the molarity of concentrated ammonia is 14.8. It has a density of 0.880 grams per milliliter. What is the molality, mole fraction, and percent by mass? Okay, so the first thing that I want to do is I want to get my moles, which I already know is 14.8 moles, and we have 1 liter of water. So let's figure out what our total solution is. So we have 14.8 moles of NH3, and we know that 1 mole has a mass of approximately 17 grams, which is going to give us 251.66 grams of NH3. Our water was 1 liter, because it's moles per 1 liter, and we know that 1 liter is 1,000 milliliters. And the density of the solution is 0.880 grams per 1 milliliter. So our milliliters cancel, our liters cancel, and this is going to give us 880 grams of solution. So in order to find out how much of that solution was water, we're going to take the 880 grams of solution, and we're going to subtract the 251.66 grams of NH3, and that's going to let us know that 628 grams of that was water. So now we can actually do some calculations, all right? I'm going to start with the backwards. I'm going to do percent mass. So we've got part over whole times 100. So we've got 252 over the whole 880 times 100 gives us 28.2 0.6% ammonia. For my mole fraction of NH3, I've got my moles, which is 14.8, over 14.8 plus, I need moles of water. So I'm going to very quickly take my 628 grams of water and divide it by 18 to get my moles, which is going to be 34.9. So now this is plus 34.9 over here. So when I do the math on that, I'm going to get 0.30 for the mole fraction of NH3. Therefore, the mole fraction of water is going to be 1 minus 0.3, or 0.7. So I've got percent, mole fraction. The last thing I need is molality. Molality is moles over kilograms. Moles of solute over kilograms of solvent. So we already know what the moles are. The moles are 14.8 moles. And my solvent is my water, which we calculated to be 628 grams of water, which is 0.628 kilograms. And that's going to give us 23.6 molal. And that's it for that problem. So the last part of what I'm actually going to discuss today is energies of solution, formation. Why do things dissolve? Well, we learned a little bit about this in another unit. It has to do with attractive forces. And it actually has to do with three things, okay? Actually, it comes down to delta H1, delta H2, and delta H3. In delta H1, we have to expand the solute. This is going to require energy. We also have to expand the solvent, which also requires energy. So both of these first two steps are endothermic, or a positive delta H. So now you've expanded the solute, you've expanded the solvent. Now the solute and the solvent are attracted to one another. This is going to be exothermic, so therefore a negative delta H. 3. If the delta H3 is not exothermic in nature, then the dissolving process won't occur. Now, the overall delta H of the solution, okay, can be positive or negative based on the values of delta H1, delta H2, and delta H3. For example, in this first diagram that you see here, and you're going to have to go over your pencil lines. I know the yellow line didn't come out in the copy because it didn't come out on mine. Here, the up arrow tells you that the delta H of both 1 and 2, the separation of the solute and solvent, is positive. And the attractive forces between the solute and the solvent, delta H3, is negative. So upon summing delta H1, delta H2, and delta H3, in this example, the delta H of the solution is negative. In the second example, your delta H1 and your delta H2 are both positive, but the delta H3 is a very small value. It is negative, it's very small. But you can see that the overall delta H of the solution is positive. And this will again depend on the nature of both the solute and the solvent. To show that, here in the table 11.3, which is also in your book, are some examples of different types of solute and solvent. So here you have a polar solvent and a polar solute. You can see that delta H1 and 2 are both large. Delta H3 is large but negative. So your delta H, your solution is going to be small because all three were large and the solution forms. Going down to the third example, when you have nonpolar solvent and nonpolar solute, your delta H1 and 2 are small, and so is your delta H3. So therefore, the delta H of your solution is going to be overall small, and the solution does form. You can see the two in between are where your solution does not form, and that's when you have a polar solvent and a nonpolar solute, or a nonpolar solvent and a polar solute. And this should make sense leading into the next thing. Factors that affect solution formation are the structure. So like dissolves like, which means polar dissolves polar, and ionic, and nonpolar dissolves nonpolar. And polar does not dissolve nonpolar. Now, why is that? Well, it has to do with a couple of things. It has to do with the structure of the molecules, which we're going to review right now, and it also has to do with the energies of solution formation that we just talked about, okay? Separating the solute into its individual components, expanding the solute, which is, endothermic in nature, as well as overcoming the intermolecular forces in the solvent to make room for the solute. So we're expanding the solvent, which is also endothermic in nature. And then allowing the solute and solvent to interact. So those are your attractive forces there. And that's your delta H3. So let's look at what happened, or just review, because you did this in Regents chemistry, between a polar solute and a polar solvent. So let's take water, which is slightly positive on the H side, slightly negative. We can draw another one here. Side slightly positive, slightly negative. And you know that if I dump salt into this, that the Na is going to be attracted to the negative side, and the Cl minus is going to be attracted to the positive side. And that's your attractive force that they're talking about there. Same thing is going to happen over here. I've got my negative Cl, I've got my positive Na, and I have that attractive force. Okay, works nicely. Nonpolar and polar. So there's a problem there. So here's our polar water again, our slightly positive side, our slightly negative side, but in comes, let's say, FF. And FF is basically nonpolar. So there is no attraction here. All right, in our last example, we're going to look at nonpolar and nonpolar and what's happening there. So let's look at oxygen. And you know that this has London dispersion forces, and you know that the electrons are constantly moving. So what happens is there is a temporary dipole, which then induces another dipole on a neighboring molecule. And so you have these temporary dipoles and created by the movement of electrons, and now you have the attractive force. So nonpolar will dissolve nonpolar. Okay, that is it for the first lesson. Whoa.